Hey, Vlad here, devinsideyou.com. Welcome to another video. In the previous video, we talked about variants, and today we're going to talk about HigherKinded types, which are types of higher kind. And since that definition doesn't really help you, let's not waste any more time and roll the intro. As always, we're in the Ubuntu virtual machine, and we have Sublime at the top and the terminal at the bottom, which runs SPTU, which is going to run our test for us. And today, the same as in the previous video, we care mostly about compiling things because we're still, in the topic of parametric polymorphism. In the previous video, we talked about variants and upper bounds, and today we're going to talk about higher-kinded types. And in fact, lower bounds are also going to play a role. And also, sort of like as a byproduct, we're also going to learn about this thing called F-Bounded Polymorphism, which we sort of stumbled on in the video about the cake pattern. As in most of my previous videos, we're going to take the problem first approach. So we're just going to keep developing our sets, and then we're going to end up in a situation where we could use higher-kinded types without actually explaining them. So we're going to end up solving that problem, and only by the end of the video, we're actually going to have a deeper discussion about higher-kinded types and why they're called like this, and what exactly they are. Now, as I already said, we're not gonna really care about tests today, so we're gonna keep running them. But we're gonna, I'm gonna press Alt-Shift-1, and I'm gonna close the test file. So we're only gonna care about sets. So what we're gonna do now is I'm gonna go to the top, and I'm just gonna scroll down a little bit and see. In the previous video about variants, we commented out this. We actually can remove it now because we're not gonna end up needing it anymore. Right, so, and as always, I'm just going to save, and the test I'm going to rerun. But as I said already, like way too many times, that we mostly care about compiling things. All right, so what we're going to do today is we're going to scroll down a little bit in the sets and look what we have, and we're going to end up noticing that two things. The first one is that most of the functions are implemented in terms of fold. Remember, first we were duplicating recursion basically in every method. Then we switched to having for each and implementing all of the methods in terms of for each. And then we realized that there's also an abstraction called fold, and then we implemented most of the methods in terms of fold. So maybe this is a sign that there's a higher abstraction hiding there somewhere. So maybe we should have a trait called foldable, and it's going to have one abstract method called fold, and then we're going to have a bunch of other methods implemented in terms of it. All right, so for example, a method like exists, or contains, or for all. Even methods like add and remove, these are probably going to be methods that are defined on every collection. So far we only have sets, but we're going to end up having sequences later, and streams and maps and whatnot. Right? For example, something like union, this is specific to sets, so this is going to stay over here. Same for intersection. The filter is going to go different, something very specific to sets. Is subset of. It even contains the word set. The word set in the method name, right? So therefore it's going to stay in the set. Now, before I'm going to start, typing ahead, I want to mention that there are basically two ways of effectively designing systems. The one is called top-down approach, and the other one is the bottom-up. And there are many angles of how one can explain what each of them mean. What I'm going to do is imagining an example, like a typical object-oriented example, which requires some sort of hierarchy, and typically, the animal hierarchy is used. So the top-down approach would be to sit down and to come up with a plan, maybe to write the plan down. And in that plan, you're going to describe how the hierarchy is going to end up looking. So you're probably going to start at the top. You're going to say, okay, so we're modeling animals, right? So we're going to have animals. And then probably we're going to need mammals. So mammals are going to extend animal. And then you're going to end up having, like, I don't know, cat and dog that will extend mammal, and mammal is going to extend animal, and so on and so on. Now, this approach has a lot of benefits. For example, it promotes communication. If you write all of this stuff down, up front, then all the stakeholders sort of know what's going on, and, everybody knows which direction the project is going to go. And also it has this benefit that if you're going to do like a really good job creating this sort of design, then you might end up giving this design to a junior, for example, and he should be able to implement this. Now the downside of this approach is that it's kind of hard to do, because it basically requires you to predict the future, right? So you're going to end up envisioning all of these branches and all of these possibilities that your design has to be able to cover, because it's not really the same thing as designing a building. Software is always going to be changing. A building is not going to change. So and also very buildings are very similar to each other. Software tends to be very individual, which is why some people prefer to to refer to software engineering as software craftsmanship, because every software that you write is sort of individual, and it's a very creative process. Now the alternative would be the bottom-up approach. So instead of starting at the top with the animal, you're just going to start working on the cat, and you're going to mold it until it's perfect, and then you're going to start working on the dog, and you're going to do the same thing. And once you're going to start noticing the similarities, you're just going to extract them into a trait. Right, you're gonna call it mammal or something like this, and then eventually you're gonna end, you're gonna create like mammals, and then fish and whatever, and then you're gonna take them all together, and you're gonna arrive at animals. So it's bottom up. Now this approach also has benefits. In a sense that it's kind of easy. You can just sort of start hacking away, and if you're disciplined, and you also follow other disciplines, like for example test-driven development, or your types are not your types. Your types are very well defined, so you're using the type system to your advantage. Then you might actually end up with something that is kind of good. And even the same goes for the junior developer. He can just start sort of hacking, and if he had some sort of help and some sort of guidance, some sort of leash, then he might ending up with a pretty good design. Now the downside of this approach is that you also might end up at a sort of like a dead end with your design. So you sort of like code yourself into a corner, and you have to have the courage then to sort of backtrack and to remove like half of your design and sort of start like almost from scratch, sort of like writing an essay. Very creative process. You sort of try something and then you throw it out and you try the next thing. So this could be costly, right? But it doesn't have to be, again, if you follow good disciplines like test-driven development, and if you are an aesthetically typed language like Scala. Now, as always, as you have seen, nothing is perfect. So a good software engineer, he should be able to find a balance between these two approaches. And this is exactly what we're going to do now. So far we have been doing bottom up, write a tiny test, implement some tiny functionality, and so on and so on. So now we ended up with this, pretty much fully functional set. And if we keep doing the bottom-up approach, this would mean that we should write something like a sequence, right now we have set, then we should start implementing sequence, and then we should start noticing that, oh, okay, so sequence also has a method called add, and also has a method called remove, it also has a method called map and flatmap, and so on and so on and so on, and then start extracting those similarities into a trait. Now this is obviously going to take a lot of time, so what we're going to do is we're going to switch gears to the top-down approach. So as I said, most of the functions are implemented in terms of fold. So what we're going to do is we're going to start by creating a trait called foldable. I'm going to put fold in there, and we're going to implement, move these methods over there, right? And then we have sort of like the best of both worlds. So let's get started. Okay, so the first thing that I'm going to do, I'm going to open the panel by pressing Ctrl K and then B, and over here where we have the set, we're going to create another file. I'm going to save it as foldable.scala, and I'm going to go back to set real quick. In fact, you know what, let's split it like that. I'm going to put foldable over here, and I'm going to keep having set over here. I'm going to close the panel. I'm going to go to the top, and I'm going to copy paste the package because we're going to be in the same package. So we're going to have a trait called foldable, like this, and what we want to have is we want to have fold. So let me press Ctrl R, and Ctrl R is going to allow me to go through the tags in the file, so through all the defs. So I can just say fold, and we're going to end up over here at the fold. So what I want to do is I just need the signature, right? So this is the signature, like that, and we don't need the final. So this is what we need. So I'm going to take the def, I'm going to put it over here, right, and it requires a lot of space, so I'm going to do that so that you see the entire fold. Now fold is parameterized with the result, right? So we don't need to do anything special for results, so it's going to stay parameterized, but it requires an element. So let's start by doing that element. Now, so this trait requires an element, and therefore it might end up being fine. All right, so it's fine, but if we try to mix it in now, so if we go to the top again, and over here we're going to say extends foldable, we're going to end up having a problem with variants, right? So we did not mention this plus, and I just want to show you that the compiler is going to notice that. It should, right? So as of right now, you see a bunch of errors, but the one at the top should say covariant type element occurs in invariant position in type element, right? And then basically it says, okay, you're not implementing fold, and then all of these methods are not compiling. Okay, so all we need to do is to have a plus over here, and it should compile. Yes, it compiles now. So as you know, I prefer to add the override keyword. There are quite a few reasons. First of all, for education purposes, so you sort of see that we're actually, actually overriding. We're not accidentally, trying to override that something that is not there. Also, it's really good just visually to see, oh, okay, so this is actually an override. This is not just a random definition, okay? Now let me point out a few things. If you put this annotation in an abstract method, it's just going to say that the implementation does not contain a recursive calls, even though there is actually no implementation, right? So let's remove that. All right, so let's continue working on foldable. So let's look at the first thing that we can move that is implemented in terms of fold. So let's see. So apply is something that is very special to sets. Contains and does not contain, that is implemented in terms of exists. So if we started to move, if I start moving does not contain, then I will end up needing to move contains, and then I will end up moving exists, and then probably I should also move does not exist, and then not for all and for all. In fact, in my preparation I didn't do it like this, but I'm pretty sure that we can pull it off. So let's just cut all of this out, right? All of these, let's just cut them out. Now, if I save this file, obviously, the tests aren't going to compile. A bunch of things are not going to compile. So let's just put it over here, like that. Let me create a bit more space. All right. So first of all, let's just see if that's going to compile. All right, it actually does compile, and that was enough. So it was just a one copy paste, like from left to right. It was kind of easy. Now let me see. So I just need to make sure that we're not mentioning set anywhere, and it turns out that we're not. And now what I want to make sure is that we're not being too abusive of the final keyword. Now, for example, does not contain is implemented in terms of contains. So I'm pretty sure that that does not contain can stay final, but contains, I don't want to make it final. I want to allow the users of my library, so somebody who is going to implement fold, which, let's be honest, is going to be me, right? I want them to allow them to re-implement contains. Maybe there's some more efficient way to implement contains or something. In fact, maybe in terms of contains, I shouldn't do that, because contains is just colon exists. So maybe it's just enough to leave exists as non-final, and to keep these, right? I think that's a bit better. And the same thing for all. So not for all can stay final. This one should be overridable. All right. So I already know which methods are we're gonna end up being able to move. But let's try to take something that we should not be able to move so easily. For example, filter. Let me cut it out. Right? So filter is also implemented in terms of fold, but it actually requires a few more things. So if I put it over here, it's gonna tell me, for example, it needs a value called empty, right? And also, like we're doing set over here, right? But we can't, set. We should pretend that set doesn't exist here, right? Because remember, we're gonna have set that extends foldable. Then we're gonna have sequence that is also gonna extend foldable, and so on and so on and so on. So over here, we should only be able to use foldable, right? So if we use foldable over here, it's also gonna tell us that empty is not defined, and also the predicate. What's up with the predicate? 29 over here. It says required set. Why does it say that a set is required? Oh, that is happening in the set file. Okay, hold up. So it's set 29. It's over here. Yeah, obviously this one wants a set, but this one is foldable. So essentially, it is not so easy to move the filter. We're gonna end up moving the filter, but not over here. We're gonna end up moving it somewhere else. So let me just press Control Z over here a few times. There we go. We have our filter. What is easy to move is for each, because remember, for each is basically the same thing as fold, just that for each is a bit more imperative, a bit more mutable, but fold is not. All right, so we can do it for each, and it pretty much can stay final. Let's have it at the bottom over here, right, for each. All right, so let's keep looking. There should be also one. Okay, so we have fold, obviously, which is the override method. And by the way, usually if you have a trait with like an abstract method and a bunch of other implementations, usually like what I prefer to do is I prefer to put the abstract things at the top, and I'm also going to try to do the same thing with the implementation. So I'm going to take fold and I'm just going to move it to the top. It probably shouldn't be like the very first thing. Maybe after apply. Yeah, over here. Yeah, like this. Okay, so add is going to end up having the same problem because add needs to produce a set, and we don't really know how to do that. Remove the same thing. Okay, union intersection are set specific anyway, which already tried filter. Difference is specific to sets. These two are specific to sets. I don't think that it makes sense to move equality because equality is different for every collection. Hash code, maybe hash code, but yeah, let's not do it. ToString is going to be different. All right, size, there we go. So I'm pretty sure that we can just move size. So we're just going to take size and we're going to put it, I don't know, let's put it at the top over here. All right, so size is only implemented in terms of fold, and it probably should be a final def. Maybe not. You know what? It shouldn't be a final def. Or maybe, I don't know, it doesn't matter. Let's not make it final for now. This is sort of like, you know, your goal as a software developer to design the system in such a way that you know, that if change happens in the future, and you pretty much can bet everything you have that, you know, on the fact that the change is going to come. So what your goal is to design the system in such a way that it shouldn't be too hard to change. It's always going to involve some effort to change the system, but sometimes it's actually designed so beautifully that that it's easy enough to change. So, you know, if we end up needing to constrain size to be final, we're going to end up doing it. Okay. Now, what about isEmpty and non-empty? I believe that we could implement isEmpty in terms of size, right? Because isEmpty, it should just say, you know, size equals 0. Let's try to do that. So let me just comment it out over here. And I'm going to say, I'm going to do that over here, right? So like being nice to our users, we can just say size equals 0, right? Because that means that it's empty. All right, it says method is empty needs override modifier. Did I not save the file? Hold up. There we go. All right, let's see. Oh, something went wrong. Let's see. A Stack Overflow error. So it turns out that isEmpty, if you scroll down, isEmpty is calling, hold up. The problem is that the stack trace is cut off, so we don't really see where it's beginning. So let's go like top to bottom. So isEmpty is calling size, right? isEmpty is calling size, and what happened before fold was calling isEmpty. That's the problem. So fold, where's fold? Fold is over here. Fold was calling isEmpty, right? And isEmpty is calling size, and size is calling fold. So this is a Stack Overflow error. So basically, what happens is that we should not just implement isEmpty. Now, this is like sort of a tiny problem, and this is a very typical problem for object-oriented design for these hierarchies. Is that, you know, like as of right now, foldable is our highest trait, right? It's the highest position in the hierarchy, right? So we sort of like envisioning in, you know, it's a top-down approach. We're sort of envisioning in that all the collections are going to implement foldable, and in my mind, like every collection should, you know, it should be possible to ask every collection, hey, are you empty or are you non-empty? So, you know, we could leave it abstract like this, right? We could just leave it abstract, right? And then we could force our implementers to implement it. Where is it? It's over here, right? So we're just gonna do, as you know, I prefer to do override like this. There you go. So we could sort of force our implementers to do that, but let's not do this now, because if we do this now, like it's not such an ideal way to have something in a trait where this trait is actually not using it, right? So if I press Control D here, I press Control D again, there's no occurrence of isEmpty. Like nothing in here uses isEmpty. So maybe, just maybe, it shouldn't be defined over here. So for now, I'm just gonna remove it. And because I'm preferring to use the override keyword now, it's not gonna compile because it reminds me, hey, you're not overriding anything anymore. All right, like this. So what's up? Did I not save it? There we go. Okay, everything compiles, and as of right now, we pretty much moved everything that we can to foldable, right? So we have size does not contain, contains, does not exist, exists not for all, and for each. Now, the next thing that we're going to do is we're going to look at it, and we're going to realize that it cannot produce sets. So all of these methods, what they're doing, like fold sort of can produce whatever it wants, right? But everything else, it just produces like very simple things, like booleans. Okay, this one is even a unit. So yeah, and this one is an integer. But none of that can produce another foldable, right? So what we should do probably is, so first of all, we could try like squeezing the necessary methods into foldable that will help us to implement methods like filter or map or flatmap. You know, we already tried with filter, but you know, look at map. Map will require that foldable has empty. Map will require that foldable has add, and map and foldable will only be able to return a foldable. We need to be able to return a set. So all of this, first of all, it's possible, and in fact we're going to implement it right now, but it's just going to impose way too many constraints on foldable itself. So instead of that, what we're going to do is we're going to create yet another trait called Foldable Factory. So the idea is that the foldable sort of acts like as a reader or as a consumer, right? So it knows how to fold through the already existing elements. It knows how to consume them. It knows how to read through them and produce a simple result like Boolean. So in addition to that, we're going to have a foldable factory. It will also be a foldable. So it will also extend foldable, right? So it will also be able to traverse the element. But while doing that, it will also be able to create another foldable factory. So let's do the same thing. So I'm just going to go over here, and I'm going to go like this, and I'm going to create a foldable factory, right? So let me copy the package the same as before, like this, okay? And we're going to have a trait called factory, right? And we already know that it needs an element, right? Because it will extend foldable, right? Was this element like this? Okay, let me create some more space. All right, so this thing compiles, but we're not using it at all yet. Okay, all right, so let's try to move a function like map to it, and then move everything that map needs. All right, so we're just going to take map. It starts over here, ends up over here, right? In fact, we're not only using we're not only moving the declaration, right? So not only copying the signature, we're actually moving the entire implementation, right? We're moving over here, right? Because every collection is going to have an already implemented map, because all it needs is fold, it needs empty, and it needs add. Okay, so let's see. So if we try to compile that, it's going to say, okay, you need an empty. All right, so let's do an empty. So it needs an empty, but notice that sats did not need an empty. Right, so the companion object for sats has empty, but the set itself does not. In fact, hold up. So because of that, we're just gonna make it empty. We're just gonna make it protected. So we're gonna have protected def empty, right? And notice that we're still using sets over here. So we're gonna change it in a second. But for now, let's do set of nothing. Okay, so it needs this. Okay, so now this thing compiles, but obviously it's not enough to work with sets. What we need is a foldable factory. So everywhere where we say set, we're going to use foldable factory. Okay, so now it's going to say value add is not a member of foldable factory. Okay, so it turns out that we also need to move map, to move add. And when I say move add, I only mean the signature. So if I copy that, if I just paste it over here, and obviously it's not going to be a set, it's going to be a foldable factory, like that, then it's going to work. Okay, now this thing is not ready yet, right? Because if we end up extending it, right? So if we go over here, so instead of extending foldable, we're just going to extend foldable factory, right? And it already has a map. So if you go down to map and just remove it, I'm not going to remove it, I'm just going to comment it out because it's already implemented over here, right? Okay, so we have 5 errors, and it basically tells us, okay, type mismatch. Come on. Oh, there's nothing there. Okay, type mismatch. So in line 17, let's go there. In line 17, we have a non-empty with an input, and we're giving it an empty. Now it thinks that we're using this empty, which is a foldable factory of nothing. But non-empty, if we go to non-empty, obviously, which is over here, it wants, at this position, it wants a set of elements, right? So we somehow need to produce a set of elements here, but this foldable factory, at least we need to pretend like it doesn't know anything about sets, right? Because if it's a set, then it should produce a set. If it's a sequence, then it should produce a sequence. So somehow what we want to produce here is not a foldable factory, it's a subtype of the foldable factory. And this is where we're going to end up needing HigherKinded types. Now, before that, let me actually go back. I'm just going to press Ctrl-Z a few times. So we have map again and we have foldable again. I just want everything to compile. So as of right now, we're not using the foldable factory. Okay, so now things are going to get a little bit more complicated. So first of all, let me write down what we already have. I'm just going to use some comments to write down this thing. Okay, so what we have right now is we have this element, right? And it's a covariant element, but it doesn't really matter. Okay. And what we want to have is we want to have a subtype of foldable factory, right? And this subtype obviously is going to use this element, right? So it's also going to have an element, right? And because it's a subtype, we want to say that it has to be the subtype of foldable factory. Now, in the previous video, we learned about the lower bound, which was written like this, right? It's this one over here. And in this video, we're going to learn about the upper bound, which is written like that, okay? So this thing has to be a subtype of foldable factory. Now, foldable factory itself, it also wants this element, right? So it's gonna, it gets a little bit more complicated, okay? Now, first of all, what does this bound mean? And by the way, I'm pretty sure that I'm gonna confuse, the lower was the upper bound. So I'm just gonna say it like once perfectly. And if I'm gonna confuse it later, just, promise me not to get confused, okay? Okay, so this one is a lower bound. This is the one that we learned about in the previous video. It says that whatever you pass in here has to be at least an element. This one is an upper bound. It says that whatever you're giving me, at maximum, it is a foldable factory. It cannot be higher than foldable factory. For example, it cannot be any. Okay, so far, these are only comments. So somehow we need to teach our type system to use this somehow. Now, where are we using element? So we're using element over here. So whatever I have written here, we should probably end up using over here as well. The problem is that as soon as I have a comma here, right? And as soon as I try to paste that over there, in fact, even a little bit before, as soon as this thing has a second parameter, this is a foldable factory, we will end up needing the second parameter over here as well, right? Over here. Now this is a recursive definition, right? So how can I paste that thing over here and then use something else over here? It turns out that this is possible, and this is called the F-Bounded Polymorphism. I'm gonna leave a link to a original paper for that. So just, you don't need to understand it at all. It's just like if you want to have like a little bit background of why it's called like this and what does F stand for, check it out. Basically, in functional programming languages, people started playing around with parametric polymorphism at some point, and the system for these types was called F. I believe it was called because it was like, I don't know, functional programming something. I believe F stands for functional. I tried to dig it up a bit, but I couldn't find it. And then in terms of object-oriented languages, like this F system was extended, and it's called sub F or F sub or something like this. And over there, you need to have this F quantification or F bound for expressing exactly this scenario, this recursive scenario. So basically, as soon as I, in order to paste it over here, I need to say that over here is going to be another this. It's weird, right? So it basically says, hey, it's parameterized with an element and a subtype of the foldable factory, which has to be a subtype, again, as I just said, of a foldable factory, which takes an element and subtype of foldable factory. I really hope that I'm explaining this, like I'm explaining this as hard as I can. I hope it makes sense, right? So now this thing is done, right? This thing is done, and if I paste it over here, right? If I paste it over here, and let me create as much space as I can, okay? If I paste that over here, I'm gonna do like extends foldable element. So we ended up using element inside of this thing now, and now we have that thing as well. So now we can also end up using that thing. So instead of Foldable Factory over here, 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 and here, we can start using subtype of Foldable Factory. So if I compile this, it should work. It did work. There was a warning. We're gonna get to the warning in just a second. For now, I just want to make this a little bit smaller, and everywhere where I'm saying subtype of Foldable Factory over here, I'm just gonna use the capital letter S, just so that it's a bit more visible for you. Let me click away so that you see what happened. In fact, like many times when you're looking at functional code, you're gonna see like just random letters used as parameters. You're gonna have like having like A, B, C, D. The reason for that is so that visually you don't confuse a type that actually exists, like for example element is a type that actually exists, and super is just like another thing that you're creating, right? So you're just giving a name to something. Like you can't change like this element to something, but you can change this one. This comes back to the notion of free variables and bound variables. So this element is bound to the scope, so you can't just you can rename it everywhere in the scope, right? So you can everywhere where it says element, I can remove it, I can rename it to something, right? But I can't rename it just over here. On the other way around, super is only available in this scope, so I can rename it only in, everywhere over here, right? So let me go back for now because I want to keep it like as readable as possible, right? Like that. Okay. So what does the warning tell us? The warning tells us that we're using HigherKinded Types. Okay, so the warning went away. So what I want to do now is I want to clean the code, right? And I want to test again because I needed to recompile so that it produces this warning, because I want to show you this warning. Okay, so if I scroll up now, okay, so this is the warning. It says HigherKinded Type should be enabled by making the implicit value scala language HigherKinds visible, and this can be achieved by adding the import clause, import scala language HigherKinds, or by setting the compiler option language HigherKinds. So first of all, at some point people were complaining that Scala was a complicated language, and a bunch of flags like these were introduced to the language so that once you start discovering like those more complicated features, you have to explicitly enable them. So at least you have a pointer like, hey, are you sure that you need that? We already had this thing with implicits in the previous video, and now we have this. I actually kind of like it. Like on one hand, I kind of like it because it sort of introduces like a little bit of gamification. It's like achievement unlock. Now I'm playing with HigherKinds, right? So if you go to the build, remember we already have language implicit conversions, so I'm going to go here, introduce another string, paste that over here. Okay, notice like before I reload the project, where the cursor is pointing to, it says this thing is a HigherKinded type. So if I reload the project and test the code again, right, so now it should, it compiled already before, but now at least it doesn't produce the warning. So let's look at this thing again. Why is this a HigherKinded type? And again, by the end of this video, I'm going to have like more like a crash course for HigherKinded types, and you will understand why they're called like this. Okay, so basically the thing is that when we're going to extend Foldable Factory, what we will end up passing over here is not going to be a set of string or not going to be a set of int. What it's going to end up being is just set without int, without string, and this is why it's called a HigherKinded type. Again, by the end of the video, I'm going to have a little bit of like a better explanation. Okay, so let me remove that. Okay, so let's start using Foldable Factory. Let's copy that. Let's go to our sets. Instead of foldable, let's use Foldable Factory, and Foldable Factory needs a second parameter, which is a subtype of Foldable Factory. Now, what is a subtype of Foldable Factory? Well, it's a set. So over here, we're going to end up using set. And again, we're not going to end up using set of int or set of string. We're just going to end up using set, and this is why it's called a HigherKinded type. So let's go down. So okay, map needs an override map, blah blah blah. Do we have map? Oh yeah, we have map. So let's go to set. Where's our map? Map is over here. Let's just remove it like that. Okay. All right. So 2 errors. It says okay, class non-empty needs to be abstract since method empty is not implemented, and the same thing for the empty run. Right. So basically, we need to go here, and we need to say at the very top, we need to say final override protected def empty, which is going to be a set of nothing, which is equals, which is set.empty. Notice that you can't use just empty here, right? Because then it's going to be a tail recursive, not a tail. Then it's just going to be a recursive call. So it's going to be an endless loop. You have to be very specific and say set.empty, even though we're importing set underscore. All right, so everything is fine now, and I don't want this video to be super long, and I've been recording already for 40 minutes. I really want to make it not longer than an hour. So I'm just going to copy fold. I'm going to cut out fold. Actually, sorry, not fold. Flatmap. So I'm cutting it out. I'm putting Flatmap into the Foldable Factory. In fact, let me do this. Okay, so paste it over here. It's a final def. Map is also going to be a final def, maybe. No, actually not. Let's not make both of them like this. Okay, so the same story. Everywhere where it uses set, it just needs to use subtype of Foldable Factory like this. All right, and it already works. Now notice one tiny thing, that it doesn't actually need a function that takes an element and produces a subtype of Foldable Factory, right? Because what it does is it calls this function with a current, and then whatever comes back, all it does with that thing that comes back is it calls fold on it. And what has fold? Foldable has fold. So it's enough if this thing is just a foldable. So this makes it a bit more flexible, right? So now we can call Flatmap on a set, for example, and give it a function that takes an element and produces a sequence, for example. Now we don't have a sequence yet, but in the future, you know, we will be able to do that. Now, as I announced before, we should also be able to move filter now. Filter, just cut it out like that. Let's go to Foldable Factory over here. Okay, so we have map, flat map. Let's put it over here. All right, so that's a filter, and the same as before. Everywhere where it says set, we're going to use subtype of Foldable Factory, like that, and now it works. And I realized that we forgot to implement FilterNot. And let me remove the final. Okay, let's just duplicate that line, and let's make this one final. And this is going to be FilterNot. By the way, these are not ideal names, because like these names are used in the Scala collection library, which is why I kept using them. But actually, filter should be called something like keep, right? Because every element that satisfies this predicate is going to be capped, right? And usually, like when you say filter, usually you want to like throw things out, right? So actually, filter not is the one that's going to keep them. So it's kind of weird. Anyway, so filter not is basically it's just gonna call filter, right? And then whatever comes in, it's just going to call predicate on it, right? And it's going to negate that, right? Because this is FilterNot. So let's see if it compiles. We're going to end up writing a bit more tests in the video about code coverage. And because we're using this parameter only once, we can actually just use an underscore here, and then we don't need that. This is not super readable for beginners, but you guys are not beginners anymore. This is already pretty advanced level. So we have filter not, filter, map, and flat map. Notice that we have add, but we don't have remove. We're not using remove anywhere here, but it's going to be a bit weird to have a factory that has add but doesn't have remove. Let's put remove there as well. So we have add and we have remove. In fact, add and remove, they have the same signature, so we can just do like that, add and remove. Like that. Maybe let's also leave a comment. Let's leave a comment here saying that technically not required, but seems plausible to be left here for the symmetry with add. Okay, so let's leave it here for now and see in the future if we end up needing it. Like this. And as you know, I like to add overrides to, okay, so this is going to be a final override, both of these final overrides, so that I'm completely sure that I'm not like overloading anything. Okay, so there we go. This is the Foldable Factory. All right, so we're done with Foldable. We're done with Foldable Factory, and the last thing that we're going to move out is going to be the factory method on the companion object for sets. So over here, we have this apply thing, and notice that it basically can be factored out. So what I want to have over here is something like extends factory of set, right? So I want to have something like this, and then this method is just going to be defined there. Okay, so this is what we're going to do. Let me comment this out. Okay, so I'm going to create yet another file. This video we're creating a lot of files. So this one is going to be called factory It's going to be a very tiny one, by the way. Right? So let's go to Foldable Factory, copy the package, right? And it's going to be a trait, and it's going to end up having a similar problem with as Foldable Factory had, but it's going to be a bit easier. So there's going to be a parameter over here, right? And we want to move apply. So I'm not gonna cut it out. I'm gonna copy it out. I'm gonna put it over here. Let's make it a final def for a change. Okay, so it already has an element. What it also needs is, okay, it needs empty. And this one, in this case, it's not a protected def. So it needs an empty, and then it ends up being in the same situation with the subtype thing. So it actually needs exactly the same subtype. Now, if I just go here and I just copy that whole thing over here, like that, paste it over here, right? I just want to stress the fact that this element is not this element, okay? All we're gonna need to tell this that this E is the same as this E, right? That is all. This one is introduced over here. Remember, it's bound only to this scope. Okay, so this one is empty, so it needs to be a subtype of Foldable Factory over here with nothing, like this. Okay, like that. And let's see how far we get. Okay, this one also produces a set. We don't want to produce a set over here. There we go. All right, so this one already works. So all we need to do is we need to go to set over here to that thing, remove that thing, and our empty is actually a final override. Final override. Now in this case, it doesn't even have to be final because we're an object, but still, I just want it to be, you know, more explicit. Okay, so now we're just saying, okay, this is, you know, the companion object of sets is a factory of a set, which reads kind of nicely. Now the very last thing that we're going to do is, if we look at the foldable factory, I'm sorry, if you look at hold on, I want it to be like this. I want it to be foldable factory, foldable, and then factory. Okay, so if you look at factory, it has empty, and if you look at foldable factory, it also has empty. I don't really like this. I haven't found like a really good way to get rid of this, but what I figured out is that what we can do is we can use the factory over the factory over here, right? So we can say that the foldable factory, it actually needs a factory, right? It's like, you know, everything is now tied together, and you know, look at this on GitHub. Okay, so because it's kind of complicated, and if I were to explain this like even more slowly, it's going to be like a 2-hour video. Okay, so let's go here, and instead of saying protective def empty, what we're going to do is we're going to say that this should be a factory, right? And everywhere where we use empty, which seems to be in those 3 places, we're going to say factory.empty, right? So over here, we obviously going to need to change the type. So this is not this thing. This is a factory of that. So this is a factory of subtype of foldable factory, right? For example, this is a factory of sets. Okay, so if we try to compile it now, obviously it's not going to compile because over here in the set at the very, very top, we're saying final override protected def empty. So what we need to override is a factory, right? And this is not a set of nothing. This is a factory of set, and it's just set, right? Because the companion object is the factory of sets, right? So I believe this is like a little bit better. It's a bit more entangled, but somehow I feel that it's a little bit better. I don't know. All right, so we're actually by the end of this video. So let me introduce, you know, let me give you like this sort of like a crash course so that you understand why, you know, all of these things are called, you know, higher kinds. And you know what? Before that, let me actually look at everything, and then I can commit it, because I'm gonna create a main method now, and I'm not gonna commit the main method anyway. Okay, so give me a second. All right, so all I want to do is I want to go to factory, and I want to just move this thing down. I said previously that I like to have the abstract methods at the top, but in this case, this thing is very tiny, and it's used over here, so I can sort of read it top to bottom. Okay, so this is all we need. So let me get out of SBT for a second. I'm going to say git status, and this time we added a bunch of new methods, a bunch of new files, so I'm just going to add everything, commit-am. Okay, so this is going to be video 8, I believe, and I'm just going to call it HigherKinds HigherKinds like this. Okay, commit, push, unlock my key. All right, so let me double check, refresh the page. HigherKinds over here. If you scroll down, you see basically we added 3 files. We changed a few signatures, moved a few things around. Yeah, actually not really big changes, but it's actually our massively powerful changes. All right, so this video is probably going to be a bit longer than 1 hour, but this was like the main thing, and if you care about the details, keep watching. All right, so we're back in the VM, so let me start SBT again. We're not going to end up using tests. We're just going to have a main method, and I'm just going to run it. So let's just create a main method over, doesn't really matter where. Let's create it over here, main.scala. Okay, so let's do object main extends app, print line, hello world, because how else are you going to know that this thing is working? And we're going to end up using our homegrown collection, so let's also import them. All right, now HigherKinds, they come from higher order functions. So instead of just the word order, the word kind is used. And whereas higher order functions are acting on values of higher order, HigherKinded types are acting of types of a higher kind. So let me just write a bunch of examples for you, and then it's hopefully going to become clear. Now I know that I'm talking too fast, but you can always like download the code, pause this video. I'm probably gonna clean this up once I finish it. I'm gonna probably put it in gist so that you can consume it at your own pace. All right, I should have probably created 2 videos. All right, so we're gonna start with an example of an OrderZero function, right? So this is a function that is present in every language, right? It's a function of order 0, so it's not a higher order. It's hit caps lock. It's not a function of a higher order. It's a function of a regular order, right? Now, in fact, like this is just a method, but we have to add an expansion that will create a function from int to string for us, right? So it's basically, on one hand, it's a method, but it can be viewed as a function from int to string. Okay, so let me compile that. All right. Let's have a few examples of that. Print line example of OrderZero function, and we're just going to give it a 1, and we're going to give it a 2. Nothing really spectacular. It's a very, very simple OrderZero function. Okay, so let's now, in fact, let's introduce my hyphens. You know that I prefer to have those hyphens here. So I want to have like 50 of them, right? And clone that, bring it down over here, right? So we have hyphens. Okay, so let me also have something over here. So now I'm going to have an example of an order1 function, right? So it's going to be a function of a higher order than 0, right? So it's going to be a function that instead of taking a regular value, is going to take a value of a higher order, right? So it's going to take a function. So what it's going to take is an OrderZero function, right? It's going to be a function, and I'm going to use these types so that I can sort of chain them together. So I'm going to say, okay, int to string, and what it's going to produce, it doesn't really matter. So I'm just for fun, I'm going to produce a set of strings, right? So now when we call an example of an order function, we have to give it an OrderZero function. For example, this one doesn't have to be this one, but we're going to use this one as well. So what is this function is going to do? The implementation is going to be a little bit random. So over here, I just did this. So I'm going to do something random. So for example, I'm just going to create a set of 1 and 2, and remember we're using our sets. We're not using the sets from the collections library, but we could use the ones from the set and collection library. Okay, so we're going to take this one and we're going to map it to this OrderZero function, right? To this one, and it's going to compile, obviously, right? And let's go. Oops. Let's have a few examples. So the same as we have examples of calling this one, we're going to have a few examples of calling this one. Okay, so we're just going to call it, right? So it's going to be example of order1 function tab. Okay, it's this one, right? And as the first, in the first example, I'm just going to straight up use this. So we have add expansion that will take this def and we'll create a function from int to string for us. Okay, so let's have this. And another example, I'm just going to duplicate that. Another example is just going to be console.yellow plus the argument plus console.reset. Oops, t. The t is capital, right? So this thing is a function, right, that takes an integer and produces a string, right? So if you're not used to reading this, it's basically the same thing as here. Input comes in, and the input is used over here, right? It's exactly the same thing. Okay, let me revert that. There we go. Okay. All right. So let's go a little bit higher, and you know, the higher we get, the more abstract it becomes and the more complicated it becomes. Okay. So let's duplicate one of these. Let's go down like that. Okay. So let's have an example. Example of order2 function. Right? So an order2 function needs to take as a parameter an order1 function. Okay, so we're going to have an order1 function. Whoops, order1 function. Right? So we're just raising everything gets raised to another level of abstraction. Okay, so we have an order1 function, and again, I'm going to keep using the same type. So it's going to be a function that takes as a parameter a function, an OrderZero function, right, which takes an int of string and produces a set of strings, right? So it gets more and more complicated, and what this is going to produce is going to be a set of string. Now it doesn't have to be, right? I can do whatever I want here, right? But in my prepared example, I'm going to produce this, right? So look how everything is getting raised. First we had an int, then we had an int string, then we had an int string to something again. Okay, so the implementation for this is going to be a little bit complicated, but basically what we're doing is a bit of a type Tetris, right? So I want to have a sequence of these functions, and then I'm just going to map them, and I'm going to apply this, right? So I need to have a sequence of these. In fact, let's not use a sequence. Let's keep using our sets. I'm going to use the set, okay, over here, right? So I'm going to have a set of these functions. So I'm going to randomly come up with functions like this. Now the first one is going to be this one, right? This is an order1 function, and the second one is going to be this one. Right? Also an order1 function. So now I have a sequence of them, and now I can map all of them through this, through the order1 function, like this. Okay, I should compile. This is basically like a little bit of a type Tetris. Now I did something wrong over here. Main 24 example of order1 function. That should have been a zero function, OrderZero function, right? Because it's basically this one and this one. Oh, and I ended up using a sequence. Hold up, set. Okay, there we go. Now it compiles. So let's have a few examples of calling this function. So what we're going to have is we're going to have a print line. We're going to have example of not one. We're going to have example of order2 function, and we're going to call it with an example of order1 function, right? This one, right? And this is what it produces. Another example of a function that we can use, put in here as a parameter, we're going to say, okay, input comes in, right? And the input is an int to string function, right? So let's call it int to string. And over here, let's just create a set of 1 and 2, and we can map it through this function, right? So I know that this is a little bit too fast, but basically it's basically a type tester. So you just look at the type and at the types, and you create something random that matches these types. Now this is exactly the same thing as just saying map, right? So it's just saying set.12 map. There we go. And as a last example, let's also do something else. So let's do map, and we're just going to map it to some parameter. And after that, we're also going to add, and we need to add a string over here, right? Because this after the mapping, it's going to produce strings. Okay, so this is the last one, which was a little bit different, right? And as a very sort of last, it's not really example, just like sort of for clarity about about the types. I'm just gonna hold up. I'm just gonna write this. So this is a composed function A, which is producing a set of strings, right? So this thing, okay, this is just that, right? That thing, okay, just so that you understand the types a little bit, right? So this is composed function B. In fact, why did I call them compose? I mean, you're sort of composing functions, but you're actually evaluating them. So the names are not really correct. Okay, so this is set of string. This one was just a set of string. So we're going to have a set of string over here, right? And this one is, let's see, it should be this one. Example of order1 function applied to example of OrderZero function. Like that. There we go. Yeah, there we go. And the last one is, it's just an int. Why am I saying this just now? Let's call it composed function, because I sort of called them like this. It's sort of weird, right? So this is the one that actually produces the string, and this is basically just that. Right, so basically I wrote down all of these examples just so that you see the types, right? So basically these higher order functions, they generate types of higher kinds. You see, like string, set of string, set of string, and this is, it just keeps going and going and going. So this is a 0, 1, 2. Okay, so now let's see the relation to types. So what we're gonna have is, first of all, I'm gonna have, let's switch to compiling now, because we don't care about running anymore. So let's switch to compiling. So we're gonna have, first is a comment that a kind 0 value can be absolutely anything, right? So any means the type. So kind 0 type is any, right? It's any type is a kind 0 type. For example, an int, string, a set of int, all of these are kind 0 types. So the same as we did with functions, let's do the same thing with types. So let's have a trait called example of kind 1 type, like this, and a kind of 1 type needs as a parameter another type, right? It needs as a parameter a kind 0 type, and I'm not sure why I said value here, kind 0 type. Now this is sometimes called a type constructor. It's similar to a function, right? This type takes as a parameter another type, and it produces yet another type, like this. So let's have an example. So we're going to have an example of kind 1 type. In fact, it's going to be an example of kind 0 type for ints, because this is an object, and an object cannot take parameters. And if it can't take parameters, then it becomes a kind 0 type. But it extends an example of kind 1 type of int. So this is another example for a char, and this is another example for an int set. So it's going to be a set of int and a char set, right? So it's going to be a char, right? So all of the types on the right are types of kind 1, and all of the types on the left are types of kind 0. Now let's get higher, right? Let's get higher. Jesus. All right. So let's have a trait, okay? That is going to be an example of kind 2 type. And it's going to take as a parameter a kind 1 type. So it takes a kind 1 type as a parameter, and because it's a kind 1 type, it's a type that needs another parameter. So we have to go here and say, okay, there will be some parameter. We don't really care about which one, but there will be some parameter. This is very similar to what we did over here with the Foldable Factory. We said, okay, so this is a Foldable Factory, right? This is a type of kind 2, because not because it takes two type parameters, but because one of the type parameters is a kind 1 parameter, because it needs another parameter, right? So it's the same, but over here we ended up calling it very specifically, right? Because we needed to make sure that this is the same, that the compiler understands that this type over here is the same type as this one over here. Whereas over here in our example, we don't really need anything that is so complicated. So this is all we're going to have. So just to have this as a better example, we're going to go here and we're going to say def map. So map is a function that takes a kind 0 type source, right? And it produces a kind 0 type target. Now, as a first parameter, it's going to take a function. Sorry, not a function. It's going to take a collection, which is going to be a kind 1 type of kind 0 type source, right? So basically we're going to say, okay, give me a kind 1 type over here, and I'm going to assemble this to a kind 0 type, right? So this one becomes a kind 0, right? Because it's a mixture of this one and of this one. Kind 0 type source. There we go. Okay, so this one and this one together, they create this type. Okay, so and then it becomes a kind 0 type again. So the collection is a kind 0 type, right? And then it will also have the function that will take the kind 0 type source and produce a kind 0 type target. Okay, and the end result of this function is going to be a kind 1 type of kind 0 type target. Okay, so we start with source kind1 type, kind0 type source, we end up with kind1 type, kind0 type target, right? By going through the collection and applying this function that will take a source, produce a target. Now let's see if it compiles, and of course it does. What we're gonna have is we're gonna implement this, right? So we're gonna have an object. I'm gonna say example of kind 0 type for sat, because it's an object, it can only be a type of a kind 0, and it's going to extend an example of kind 2 type, okay, and it's going to pass in a sat. Remember, the same as we did in our sat over here. You know, when we extend it, just sat. It's not a set of string, it's not a set of int, it's just a sat, because a kind 2 type wanted a kind 1 type, and a sat is a kind 1 type. Okay, so now let's do final override def map, and let's just copy that. In fact, let's copy all of this. Let's copy all of that, paste that over here, right? And now everywhere where it says kind 1 type, notice that kind 1 type is not specified anywhere over here. It was over there, but over here it's a set, right? So kind 1 is a set. In fact, by the way, we can also rename this to set, okay? So set comes in of a source type, and a set of a target type comes out. Now, how we're going to implement this? Well, very simply, we're just going to say set map function, right? And this is how this whole thing works. So now what you can do is you can just copy that, right? Paste over here, and now everywhere where it says set, including the name. Okay, maybe not this one. Hold on, I'm going to keep calling it collection. Hold up. Collection. Okay, so now everywhere where it says set, we can literally use anything that has map, right? So we can do option, right? Option has a map, so we can, you know, with this signature, we can go and do a collection from the standard library, right? For example, instead of option, we can do sequence. Oops, forgot about this one, sequence. There we go. Right, so this is Scala collection, immutable sequence, and so on and so on and so on. Okay, now another example of this would be a bit more similar to what we did was the Foldable Factory, because it was a Foldable Factory. One type was fixed and the other one was not. Right, so in the Foldable Factory we also had the element. We already fixed this element, so we don't have an underscore here. We have it over here. So I'm just gonna show you an alternative of doing that, right? So I'm gonna say that it's gonna be example of kind 2 type, right? I'm gonna call it with source parameter fixed, and this is going to be a bit more similar to object orientation. Okay, so what it's going to have is it's going to have this fixed kind 0 type source, right? And after that, it's going to do the same thing as over here. Right? It's going to need the kind 1 type. Now this is very, very similar to our Foldable Factory, right? So if I go there, it takes an element here, and then it takes subtype of Foldable Factory. Now this one is even more complicated because it uses the F-Bounded Polymorphism. In this example over here, when I'm gonna end up needing it, this is exactly why I'm doing this thing, because this is like more like a crash course, more like a simple like step-by-step thing. With the other one, we just had a problem, we needed to fix it. Okay, so this trait is also going to have map. Okay, and this map is going to have only one parameter because this one is already specified over here, right? So let's go over here. Let's go over here, right? And so this thing is going to be mixed into a set, right? The same as we mixed the Foldable Factory into the set. So we don't need to pass the collection. We are the collection, right? So this is going to have just this one, okay? Like this, right? Now, if I wanted to implement that, we would need a class. In fact, you know what? I'm going to make it an abstract class. I'm going to make it an abstract class, right? So this is going to be sort of like a middle step, so that you see like this object orientation, this environment model of computation, this all like mixes, you know, blends together over here, right? So we're going to have over here, it's going to be called example of kind 0 type for set of t with source parameter fixed, right? So it's going to take a kind 0 type source, and this is this t, right? This is this t. I'm just going to call it kind 0 type source. Now it extends this thing that we just created, right? And I'm just gonna put it over here on this line because everything gets like freakishly large, right? So obviously it's gonna pass this one over here, right? And as I already said, we're gonna do it for the sets, right? So we're gonna have sets over here, right? Now, as I said, this is going to be the thing that is a collection. Because I don't want to implement the entire collection, what I'm going to do is I'm just going to say, okay, this thing has to have a collection. Okay, this is a collection, which is a set of a kind 0 type source, right? It's a set of kind 0 type source, right? So that when I'm overriding, hold up, final override, right? So when I'm overriding this thing over here, right, everywhere where it says kind 1 type, I'm just going to say set. Okay, and the implementation is going to be exactly the same. It's going to be collection map function, right? So this is exactly the same thing as this one, right? So hold on, let me move it down like that. Okay, so these ones are virtually the same thing as these two. Okay, and hold on, let's do that. Okay, so maybe you can pause the video over here. So these two are virtually the same as, I'm sorry, god damn it. Okay, so these two are virtually the same as these two, but this one is more functional and this one is more object oriented, right? Because object orientation works more with the environment model of computation. It wants more things to sort of just float around in scope. All right, so now I know that this video was like super long and kind of complicated, and I explained it like way too fast. But somehow, you know, when I'm writing scripts for these videos, in my head, it's actually not that much information. But once I start talking about them, I don't know, somehow it gets longer and longer and longer. And this time, you know, I sort of planned to make only one video, and then somewhere in the middle, I decided, you know what, I'm just gonna stick to it. I'm just gonna do it. Okay, so I'm sorry for talking so fast. I'm sorry for explaining such a complicated topic so fast. So what I'm gonna do is I'm gonna clean this up, and I'm gonna create another probably a gist and upload it. I'm gonna leave the link down in the description. You know, the link to the commit is also in the description. As always, the link to the entire project. All the links are gonna be in the description. And I hope you like this video. And don't forget to like it. It really helps me out a lot. Subscribe if you want to improve the developer inside you. Most importantly, take care.